listening to the Thesis Review podcast. I'm your host, Sean Wellick. On the Thesis Review, I'll interview researchers from around the field, centering the conversation around their PhD thesis. In addition to exploring the technical content, this will give insight into their history as a researcher, allow us to revisit older ideas, and provide a valuable perspective on how their research and the field itself has evolved since their PhD days. How do we make machine learning training and deployment efficient and scalable? This question sits at the intersection of machine learning and systems, and today's guest is a pioneer in this area. My guest today is Tianqi Chen, an assistant professor in the machine learning department and computer science department at Carnegie Mellon University, and the Chief Technologist of OctoML. Tianqi's PhD thesis is titled Scalable and Intelligent Learning Systems, which he completed in 2019 at the University of Washington. We talk about his influential work on machine learning systems, starting with the development of XGBoost, an optimized distributed gradient boosting library that has had an enormous impact in the field. We then discuss his PhD work on deep learning frameworks with MXNet and machine learning compilation with TVM, which enables deploying machine learning components across diverse hardware platforms. There's a lot more, including how often he writes code, his thoughts on systems and generative AI, and of course, great advice for new researchers at the end of the show. The Thesis Review is available on SoundCloud, Apple Podcasts, Google Podcasts, and Spotify. If you're enjoying the show, please leave us a 5-star review on Apple Podcasts, and be sure to follow us on Twitter at Thesis Review. To support the podcast, go to patreon.com/thesisreview, or make a one-time donation at buymeacoffee.com/thesisreview. Here's Tianqi Chen with Scalable and Intelligent Learning Systems on the Thesis Review. So thanks so much for coming on the Thesis Review. So before we dive into your PhD work and what you've been doing afterwards, why don't we go back to how you got started in research and even in programming in general? Yeah, how did you get interested in doing research and then eventually in deciding to do a PhD?
Yeah, so I still remember it was like a third year in my undergrad, and then at that time, we were starting to try to go into find research opportunities with some of our professors. And at that time, I think machine learning was kind of a bit well known, but not as hot as today, right? But then I started to say, oh, the term machine learning sounds interesting. I still remember reading this textbook from Tom Mitchell, which is part of CMU. MLD founders, and we find that okay, this seems interesting. It's really fascinating that machine can learn so many things. So that's how I got started, in my third year of undergrad, and then I've been working on this field since then. Of course, working on different topics from more algorithm part, and later, more recently, I'm focused a bit more on machine learning assistance. Yeah.
Mm-hmm. Back then, could you have kind of envisioned that you'd be working on the area that you're working on now?
Yeah, I think there are a bit of I think it's very there's a bit of connection point at that time when we started to work on when I started to work on the rate areas. That was a time where I think deep learning started to popping up, but we are not yet at the ImageNet moment. So there are papers about uh, restricted Boltzmann machine now, like on major conferences. And at that time, one of the things that I spent most my undergrad, and then I did a master before I got my PhD. So actually, almost a quarter, three quarters of my master time as well, working on building deep learning models. And at that time, actually, we had an ambitious goal, like we want to use the deep learning model then, the convolutional restricted Boltzmann machine, to train them on ImageNet. And very naturally, like you face problem because the problem then is that everybody's working on MATLAB at that time. And of course, you cannot build your deep neural networks on MATLAB, and so I had to learn CUDA programming from scratch, and it took me about, I think, 6 months to build that one model. And what's oh, and it's getting accelerated, runs on CUDA. I have to write all the convolution code and so on. But it didn't work out at that time because the model that we picked, the residual Boltzmann machine, was not really the I think it's not really the right model. But that was a very fun experience. But it's a bit frustrating. But I think that's also what gets me interested in this problem of how we can accelerate innovation, right? Today, with the frameworks like PyTorch and TensorFlow, you will be able to do what I did 10 years ago in maybe a week, right? Instead of 6 months. So really, a lot of this is thanks to the development of machine learning systems. So so that was a start, and then um, I think near the I think in my last year of my master, I'm getting a bit nervous saying that this deep learning direction is not paying off. So at that time, I started to work on something tangential. So there was a KDD, this conference on knowledge discovery. They had a data science challenge for, I think in that case was music recommendation. I was aware like Ruslan, who is also at CMU, interestingly, he had an early work on residual Boltzmann for recommendations. So I started work on recommendation models. Of course, the residual Boltzmann machine itself is not that helpful, but we then started work on matrix factorization variants and so on. And then we won the third place in that KDD Cup, and that's where it's kind of first positive feedback then. And then I applied to as a PhD degree, and also wrote a similar paper following that particular work, and that gets me to the States and to Washington, actually working with Carlos, who is now at Stanford. Yeah, so
Mhm.
yeah.
Yeah. Yeah, your thesis had kind of maybe 4 different sections, but kind of 3 different themes, and, the first one was on the model called XGBoost. Um, so as you were mentioning, it was kind of unclear at the time where deep learning was gonna play a role. Yeah, I mean, in a lot of situations, things that don't involve deep learning can often perform, really well. But yeah, I'm curious from your perspective, kind of what was the backstory of starting to work on XGBoost, and then obviously, yeah, kind of what is XGBoost?
Yeah, so XGBoost is this I think it's an efficient, scalable gradient boosting framework, right? And that implements a variant of gradient boosting algorithm. And it's a very traditional algorithm used invented by statistics community during Friedman, and actually it's pretty powerful. And so the backstory is also quite interesting. So when I get to Washington, at that time the MXNet happens, right? We know that deep learning started to take off, and but at that time, one of the things that I'm really interested in, and also I try to bring my advisor, and he seems to be pretty interesting as well, is that we want to challenge the deep learning, like why is deep learning successful, right? So at that time, our hypothesis was deep learning is successful, of course, because of the one hypothesis is because of a deep neural network, right? You get deep neural, they have very powerful capabilities. But another factor would be, you just get a bigger data set, right? You want to be able to get your model learn from bigger data set. So our hypothesis was if you bring some of the other models, like either kernel machines or tree-based model, and let's throw bigger data set at it, will you be able to get as good as deep learning? So that was like a initial thing, that goal that we want to try to set out to challenge deep learning. So and then we started looking into different models. Actually, initially, my advisor he thinks that kernel machine would be better candidate. But then because I had my past experience in KDE, and at that time when we do data science challenges, we build a gradient boosting variant and found that's pretty powerful. So I feel like tree-based model have great potential because they have this ability to grow your model space, right? Your it's not fixed set of parameters depending on depending on your data, you can introduce new cuts and you can combine those cuts together. So it's pretty powerful. So our I want to say, if we build a scalable tree algorithm, will they be able to compete with deep learning? And that was the thing we set out to do. So, but then the problem then is that we cannot find a very scalable solution. Now there are decent solutions, but they don't scale to the data set that we are looking at. And I had to work with a CSE cluster, running experiments on a lot of things, and I find, okay, it seems that we need really a good scalable solution. So that was kind of motivates me to start to build XGBoost. And a lot of it involves both algorithm implementations, like a lot of at that time, if you encode your model, right, you have dense component, but you also have one hot encoding that's sparse, right? So it have optimizations to try to be smart and not trying to trying to handle sparse data pretty well. Another thing that we did is we find that in a lot of cases you have missing values, and instead of imputing, the tree will automatically learns, you know, what is the ideal direction that you go to when you are missing. So it's kind of learning best imputation strategies from data, and then and we also build system optimization, so introducing multi-cores and making sure it's cache local and so on. So we did it, and then actually in our evaluation, we for some settings where we kind of do well, but we kind of know we didn't achieve the original goal of beating deep learning, at least on image data set. Right? Image data deep learning is still king in the hell, but it's a very interesting byproduct in the sense that we build that, and at that time, I have a few friends that were also working on data science competitions, in particular Kaggle competitions, and we tried this tool and it seems to be pretty useful. And my friend convinced me, why don't you release a Python package that all this? So we did that, and I also started work with because the different demands, we also started work on R package and language mining on different fronts, and because at that time it was like a 5 times or 10 times faster than some of the other solutions out there. So it's really quickly take off. And people started to use it, and now even today, according to Kaggle, is still one of the top 5 most widely used data science package out there. So it's kind of like a very nice surprise, and in the end, well, I think we kind of achieved the goal in a sense that um, although our original hypothesis is, if you build powerful tree-based method or even on image data, you might be able to beat deep learning, but it turns out it doesn't. But on data like tabular data, it really shines, and still today, like it's a go-to method that people deal with tabular data set. So in some sense, being able to scale the tree method on bigger data set do help. Uh,
Mhm.
yeah, although
Yeah.
it was not what we expected initially. Yeah.
And it seems like, so at the beginning, it does have this flavor of like the pattern we're seeing today, where you kind of identify a model class that has some knob that you can turn, and the knob that you can turn relates to like adding more data, adding more compute. And so you were kind of exploring that in the context of these
Yeah.
tree-based models.
Yeah.
Yeah. And then I'm curious, like, so then this turned into research problems that made into your thesis. So was it a case of like you had this goal of kind of scaling up these models, and then saying that is really, it sounds simple when you say it, but then as you actually go to do it, you discover there's all these interesting systems challenges to it.
Yeah, it's more like a problem driven, right? Like we had
Mm.
a problem of, we want to scale the model, and then of course we can try to take algorithm approach as well, right? And in the end, we find that system approach is also very important.
Mhm.
So it's kind of a bit both, yeah.
If you look at this project, are some aspects of it machine learning problems and some are systems problems? And maybe just as a more general, higher
Mhm.
level question, like as you do your type of research, do you kind of make this distinction between systems and machine learning, or?
Line is blurred a bit more, like, and I think there are different kind of researchers. Like, for example, there are more like methodology driven researcher, right? If you are working on particular methodologies, There are experts working on convex optimization, or experts working on maybe generative modeling, right, and so on. So I think that that's a totally viable research style, and a lot of researchers are successful, working on specific kind of methodologies and area as well. In my case, I will categorize myself a bit more like a problem driven. So I'm interested in a problem. The problem is, I want to make machine learning I want to make machine learning systems, AI system that works. And then we start to ask what are the methods we need to solve this problem. And usually it comes down to a combination of algorithms, systems, and sometimes even lower level, right? And it's becoming more obvious nowadays with the bigger models that definitely the consideration of compute and data have to be factored in, right? So and it's also kind of like a when I was doing my PhD, it was not so obvious, but now there's this emerging subfield called machine learning assistant, where we
Mm.
kind of start to take this holistic approach to think about tackling these problems. So I would say I think my research style is a bit more like that. So looking at problems and ask, what are the necessary tools we need to solve them, and trying to attack it from a holistic angle. Yeah.
Hmm. Yeah. Yeah. In the next part of your thesis, you're moving into the deep learning world. Yeah, it's about the framework or yeah system called MXNet. So did you want to just talk through yeah kind of the transition, or I'm guessing this was chronological, like you did XGBoost first, then MXNet,
Yes. Yes.
but yeah,
Uh,
how you started working on
Yeah,
MXNet.
so after we did XGBoost, one of the things that I always wanted to come back to deep learning. I had this unsuccessful experience in my master and undergrad, and now there's the boom of deep learning uh, success, right? And I really wanted to come back, and I still had that passion, except that at that time I had to work on something else. Uh, to graduate and build a track record then. So that was like actually while I was working on XGBoost, I started to talk to certain friends, and we started to think about, hey, what other things we can do in deep learning, right? So at that time, I think it was initially Alex have a framework called CUDA-ConfNet, and then there's a system from Berkeley called Cafe coming out, and we feel like there are still a lot of things that can be done on building scalable models. So how can you do at that time it was more like a AlexNet, right, or VGG, like how you can scale it up onto multiple machines. And also I did had a my experience also unsuccessful in the past helped, because I did build all those CUDA kernels and so on, so I kind of know the complexity there. So that gets me into building machine learning frameworks. So
Hmm.
MXNet was the framework that I worked with Mo Lee, who was then at CMU, and he moved on to Amazon, and a few others, to build up an open source project that with the goal of being able to build things as computational graphs to automate differentiation, and also have accelerations using CUDA.
Hmm.
So that was a time where I think uh, the deep learning framework, right? It kind of started evolve. Start from Cafe as the first generation. At that time, the first generation framework don't necessarily have the concept of things like automatic differentiation. It was like still backprop, so you cannot do the things like gradient of gradient. There's less optimizations, and there's also not a lot of principal concern on how you can, for example, using multiple GPUs to train the model and so on. So we put quite a bit of work on making a framework that actually help you to scale up to more devices and so on. Yeah.
Hmm. Yeah, that's really fascinating that you had kind of been working on the CUDA kernels. I guess that was before AlexNet.
Yeah. Yeah.
Yeah,
Exactly. Yeah.
and then it turns out to be like a very relevant skill set then.
Yeah.
And then yeah, another personal note, when I first started my PhD at
Mhm.
NYU, I was actually working with ZZ.
Oh, nice.
Um,
Yeah. Yeah.
and so yeah, he was on MXNet and then he went
Yeah.
to Amazon. So yeah, I remember reading through the MXNet code actually back then. And
Mhm.
so MXNet I guess had this there's this distinction between like imperative and symbolic. Yeah, could you just talk a bit about that? Because I guess this was one of the kind of key features of it, that it supported both of these paradigms.
Yeah, so I think nowadays, right, we are very getting used to PyTorch, where most of the things are being imperative. So the advantage of being imperative is that you can just go and you run things, and you'll be able to see the immediate output of a result. But then there's also another thing that's in the back that if you really wanted most of optimization, you want to be able to capture the bigger set of a computational graph, and which we call, well, at that time we call it symbolic, right? You will be able to capture, define a graph so that you can do a bit of more holistic optimization.
Hmm.
So in that time, we are really focused on how we can get the good performance without sacrificing flexibility, right? So at that time, we started work on what we call hybridized mode. Allows you to, for a certain subset of computations, you define it as a symbolic, but you're still able to embed it as a part of bigger imperative optimize program. So at that time, actually, MXNet, for quite a bit of time, it's getting like at least on my GPU, it's getting the state of art performance. NVIDIA have been using it for their benchmarks for quite a while to indicate the best performance you can get on multiple GPUs. And you find that actually that particular pattern still exists. Like nowadays, if you start looking PyTorch, they are starting to bringing back this what we call tracing and compilation, right? Which is kind of is reflecting the imperative and symbolic paradigm we have.
Looking back, was it, how do you view the choice to do both at once? Was it a kind of good decision, or?
Yeah, looking back, I find that in a lot of cases, at least in the deep learning frameworks, right, first things people care about, we realize is that people care about usability, right? So I think at that time, PyTorch's choice of imperative certainly is the right choice. And then there's a question about how you once you get that, how do you bring up still hide, right, some of programming like symbolic choice that allows you to do optimization. But if you are starting to have needs like bringing in your models onto mobile devices and other environments, you will start to find that still the ability to be able to represent the entire combination graph, a big chunk of it, is still very powerful. And even today we are still using that in things like Onyx and a lot of other things. So I think this trade-off still exists and still going to help us designing deep learning frameworks. Yeah.
Hmm. Yeah. And yeah, I remember at the time there was a project called MinPy,
Hmm.
um, that was trying to bring the kind of dynamic computation graph,
Exactly.
and it
Exactly.
was like right before PyTorch got released. Maybe you already touched on it a bit, but now that some time has passed and now that these deep learning frameworks have kind of taken off, did anything kind of surprise you about their development? Maybe that like so many people would use a framework like PyTorch, or yeah,
Yeah,
just
yeah.
could be anything.
I think it's really amazing. Like, and I'm still working on this relative field, right? And it's amazing that how this framework can help to catalyze the really innovation, right, in the field, because the ability to be able to compose ideas, for example, so that previously when 10 years ago, it's really hard to imagine that when you developed a new algorithm, right? You kind of need to do differentiations manually. You derive your update rules, and then you write everything, right? But today, what you do is you developed maybe a part of layers, then you use Atom from existing PyTorch package and use SSD loss function or other loss function from others, and use a data loader from another people, and you compose it together and you test your hypothesis, which is much more productive. and
Hmm.
and it's really fascinating to see how this frameworks enables productivity and help us to innovate.
You mentioned like making optimizations over your computation graph.
Mhm.
And yeah, I guess in general, you might want to potentially like automatically do different optimizations. Yeah, I guess maybe this is the area where the third project came into play, called TVM.
Yeah, so when I was working on MaxNet, um, I think we did get quite a bit of help from Amazon, right? So it was a decent team, but it was not as a big team compared to other players in the field. And one of the things we struggle a bit is that there are so many operators to support in order
Mm.
to build a different framework, and so many, and also backend, right? At that time, of course, NVIDIA is the only backend that people care about. But if you start to think about things like doing operator fusions and doing layouts and so on, the combination really runs out of hand. And I feel at that time, I remember it was GTC, and it was we just get on stage and presented MXNet and to people, and I get down the stage and start to think about what I do want to do. Is it really sustainable? Like it's hard to. We have been working so hard on building all those operator coverage and things. So then it comes a question about is it possible to really accelerate that development,
Mm.
and so that a few people will be able to do something that a team that will require a team, and how do you or I'm also started interested in started working with computer architects, so developed a new accelerator architecture, and key challenge people facing now is you don't have a software stack, so and the cost of bringing up such a stack is really high. So
Mhm.
these are the pain points, and that motivates me to think, okay, we should need some more automated approach to solve this problem. So
Mhm.
that's when we started work on TVM, and that was a project I'm still working on right now. Like I think it's have been 5 years, like more than 5 years,
Mm.
maybe 6 years now. If we start to count from the beginning of a project. So at that time we started to say, okay, can we do automatic code generation? And and uh, a lot of it we find it borrows a lot of ideas from compilation community. That's why we call it machine learning compilation in general. But
Mm.
also we need machine learning in a sense that you know a lot of the original optimizations are done by human, and in order to reduce that effort, we want to be able to let the system to figure out what is a good choice of things like how do you pick your layout and how do you compose those kernels. So we are leveraging things like a MO guided cost function to measure potential costs and build search method to find different set of combinations and find good kernels that runs on the hardware of interest.
Mm.
So yeah, so that was motivation to start on the project. And when we get started, I think compilation was not that common in the context of machine learning framework. I would say the earliest pioneers would be Ciano. That was a framework from University of Montreal. They did have a compile. They are invoking compilations, but
Mm.
I think they suffered a lot from like a time to compile and so on. So I think we were kind of one of the earlier workers or works on bringing ML compilation. And it's also really interesting to see some of the concept take off. Like for example, more recently, PyTorch started to adopt PyTorch compile,
Mm.
right? And a lot of the works that we did actually did help. Like it helped us to be able to build support for more models and more hardware backend with fewer engineering effort that are reasonably manageable by a small team. Yeah.
Mhm. Yeah, that's really cool. So could you, like, for those who aren't familiar,
Mhm.
could you maybe talk through like an example of kind of starting off at the highest layer and then where this compilation step
Yeah.
occurs and like what it's doing?
Yeah. Normally, what you do is you start with your model, right? You can encapsulate, you can capture most of the computation in what we call computational graph, where it will describes the input, your intermediate layers, the linear transformations. Today, when you are talking about language models, there'll be attention layers and so on, and softmax, right? And for each of the computational graph node, you can do things like a joint transformations. For example, I could change my layout, like you could place your channel dimension in different ways, right? Or in certain cases, you might want to pad your data a bit to make sure it's multiple of something. Like these are, and also another common optimization people do is operator fusion. So you can take an operator, for example, a matrix multiplication, and you can fuse a lot of the follow-up operators like ReLU and other operators into a single CUDA kernel, so that you don't have to launch multiple ones. So there are optimization you can do in what we call graph level, and also But for a typical single operator, for example, a MATML, right? There's a question about if you want to offload it onto your phone or onto your laptop, what is the best strategy? And originally, you will need to manually write library to do that. So in this case, there's a second level which we usually call tensor program level or loop level, where you represent the computations in loop nest, and then you can start to transform a loop nest to what we call doing like a loop tiling, so that your visit of data is being local, and you can vectorize them, making use of parallel computations and offload some of that to GPU. So these are like the tensor level optimizations that we can do. And a lot of our TVM's optimization also focus on tensor level. We also build infrastructure to take the computations and and take computations and try to map those computations onto the environment that we're interested in. Yeah.
Can you actually view this compilation process as a machine learning problem in the sense that like you want to find the set of transformations that minimizes
Exactly. Exactly. You
runtime
can
or something?
formalize this. I think there are two questions, right? First of all, you need to be able to formalize the search space,
Mm,
where for a given initial loop nest, what kind of transformation you can apply, right? Because the search space will decide whether or not the possible optimizations is in your space, right? But one of the questions, how do you construct a search space? But assume that you can construct a search space, then it becomes a search problem, right? So you want to, within the search space, you want to find a point program that optimizes for certain metrics. That metric could be minimizing your running time. In that case, what we do is we can build a cost model that estimates that time, and then we will build a automatic search action that transition that searches over the space, do the measurement, and use a predictor to guide our search. Yeah.
hmm I see. So in practice, like how much is still kind of hand coded versus being automated in terms of like the optimizations that are performed?
Usually, the search space itself, right, we still hand code the search space, which
hmm
means that for this loop net, you want to tie it in certain ways. You want to be able to try it from different locality patterns. But the specific constants, like uh, here's the factor of loops that I want to split on. These are the things that you can decide automatically. Yeah.
hmm I see. Okay. And then, you mentioned that you're still working on TVM. So, I guess I had two questions. One is like if you can look back and see kind of what made it successful and what made it a project that kind of lasted beyond, a paper or initial demo. And then, maybe as part of that or after, just like how has TVM evolved since your PhD work?
Yeah. So I think since we started to build XGBoost and MXNet, I always find that I wanted to build something that people can use. So we did spend quite a bit of time, building up open source community around it and building things beyond the project.
Mm,
And TVM since then also evolved quite a bit. First of all, the world of machine learning have changed quite a bit, right? From the original more like static models to today, a lot of things are focused on transformer type models and other models that have like things like dynamic shape and so on. So we will need to be able to capture the lessons we learned in early days and being able to evolve the framework to capture those properties. We also find, I think the one reason why I still find this area of ML compilation exciting is um, the system factor is becoming much more important today than what were before, right?
hmm
Because you need really to bring those models on so many environments, and the engineering cost is high for that. So a lot of the things we are working on is thinking about how we can build a reusable framework so that you can enable better portability, how you can build abstractions such that it captures the latest hardware abstraction so that your work can when you build a solution, for one generation of hardware, you can easily port to next generation, for example. Or when your solutions work for latest generation, you can also make use of resources that are earlier generations. You don't have to throw your older GPU away. So
Hmm.
these are the things that I still find exciting. This year, a lot of our focus has been on supporting foundational models. So we have been working on this project called MOC that helps you to take language models and deploy it onto environments like web browsers, laptops, phones, and we believe like that have opportunity to unlock quite a bit of interesting things now that you can run those models locally. Yeah.
Hmm.
Yeah, native
Yeah.
fashion.
Yeah. I think a lot of people have become familiar with the problem space now that you can easily download a language model and then
Yeah,
see how slow it is if you kind of do it in the vanilla way.
yeah,
Um,
exactly.
you could see a project like Llama CPP, uh,
Hmm.
and this like quantizes the model and yeah, gained a lot of attention because then people could
Hmm.
run
Yeah,
the Llama language model on their laptop.
yeah.
Do you see TVM playing a similar role where it kind of enables you to run a very large model on your, yeah, kind of an edge device, or are these kind of in separate spaces?
Yeah, I think they certainly play quite related roles. For example, the MOCLM actually, we we also allow you to directly run those things. There are a few things that we can do the Llama CP cannot do right now. For example, you can run it on browsers
Mm,
and iPhones, iPads, and so on. And on some of the existing platforms, you also compare with Llama CP, and we can get better performance. From an
mm,
engineering approach point of view, we are leveraging what we call ML compilation. So the cost of bringing in a new hardware back and a new model will get lowered once we constructed the overall infrastructure. So we believe that there are also a lot of exciting opportunities here on bringing in a new more model support as well as more backend support here. Yeah.
mhm. Yeah, there's a lot of attention in general on language models, and so kind of each subset of research is getting a lot of attention. And so
Yeah.
one of those is systems, especially
Mhm.
because uh, we need to scale the models at training time, and then we want them to run fast at inference time. So I'm curious, like from your perspective, given all of the work that has been going on, what do you see as kind of, yeah, interesting bottlenecks or interesting areas where we can keep optimizing or developing further from a systems perspective?
Mhm. Yeah. So from system perspective, we want to be able to um, there are quite a few things that are interesting. First of all, I think this area of ML compilation is still very interesting. It
Mhm,
allows you to think about, how do you holistically think about, things like different device environments, doing things in a joint fashion, right? And also bringing in, bringing in, different model components, and also thinking about things like dynamism, both in terms of shape dynamism, but also in terms of, for example, if you are starting to think a mixture of experts, right, there are also control dynamism there. So I
mhm,
think the system problem in terms of abstraction and the scaling and inference is certainly very interesting.
mhm,
There's also I think it's also very interesting to start to think about, what are the new, I think, frontiers in the overall language models, right? Either agents or being able to do multimodalities are very interesting, and they also, or retrieval augmented generation, and likely they will also bringing in new demands on how do you build things
mhm.
together. So yeah, so overall, I think it's the first year of the Gen AI in some sense, and it's really exciting to see where it's going to head. Yeah.
Maybe just a few like fun questions. So
Mhm.
since this area involves, actually writing code and having things that run and that people use, writing code, like doing really high quality engineering is important.
That's right. Yeah.
I'm curious, like throughout your career, maybe just talking about PhD and then post PhD, what has been your ratio of kind of actually writing code versus thinking on pen and paper?
I think writing code will at least take half or if not more of the time. I know it's not typical, like not all the researchers are working in that style, but personally I find that the engineering is definitely critical to be able
Mhm.
to get things done and making sure that the project are connecting together. So from my end, I do spend a lot of time writing things, and of course, we still need to go and learn about others' work, right? Think about new research directions, and they also take time. And also, more importantly, it's not only about writing code, but thinking about architecting, right? How do you
Mhm.
build the architecture that can last and maintainable for quite a bit of time? Yeah.
From my perspective, these actually all three of these projects, they're kind of like large projects. And
Mhm.
so I'm curious, like, yeah, there's always this distinction between academia and industry.
Okay.
And a lot of the times on the podcast, it's about like choosing, you know, different problems. I'm
Mhm.
curious in terms of like setting up a team to work on a project like this. Do you kind of think about different things for academia versus like here's what we kind of want to set up for an industry team that has more people? Or yeah, does this kind of distinction
Yeah,
come up in your work?
this year is. I feel like that academia certainly have, well, in terms of resources, right? Academia is certainly under resourced, so we cannot work on. So we there must be something that something interesting. For example, the reason why I'm still excited about machine learning compilation is I want to be able to work on things that automate more, so that one
Mm,
person can solve problem that otherwise would need a larger team to solve. Um, And another thing that I think is really helpful is open source, right? So open source is a way for academia to create amplified impact.
mhm,
Where of course in this space, I think definitely will both need help from industry and academia, and then there are different valuable styles. But personally, I find that indeed in a lot of cases, it's very important to have open models and be able to build system support for them, so that academia research can continue to bring contributions to this field. Yeah.
mhm. Yeah. And then last one before we go to the last two questions I
Mhm.
always ask. I am curious, what is your favorite programming language? And has it changed over time?
Oh, I see. I see. Also, it's true, right? So I program a lot in C++, and there's something I need to get things done. And Python is certainly, certainly is something that is pretty useful. So that's why most of the project we do now, we do C++, but we also have very flexible FFI that allows you to connect to from Python. Yeah.
Mhm. Yeah. Well, yeah, this was really fun, going back, going through your thesis, and then talking about how it's kind of led to what you're working on today, and this really exciting area of ML compilation.
Yeah.
You actually have a course on ML compilation, right?
Yeah. So
Yeah.
I built an online course called MOC, and it's all in MOC.ai. And I'm also trying to, polish the course material and see if we can use that for some of CMU course as well. Yeah.
Hmm. Cool. Well, yeah, I'll link to it in the podcast notes. Um, and so there's two questions that I ask on at the end of every podcast. The first one is about objective functions.
Okay.
So, if you could view your PhD process as being kind of optimizing some objective function, what would you say that it was? Was it kind of curiosity, working backwards from some maybe career goal? And would you say it's different nowadays?
I would say on one hand, one can say that you want to go for impact, right? Because impact in that impact means that you want to work on something and you want to making sure that it can help and impact more people. But it's really hard to know in the beginning, like when you're committed to a project, whether or not it's going to lead to impact,
Hmm.
right? So I think another way that I usually say it is that I want to. It's more about also about convincement, like or if you have estimation of uncertainty, right? It's the upper bound of things that you really like, and if the upper ceiling is high, that is something that I would love to go for. Or
Hmm.
another way I ask, if I usually ask myself, if I start a project, ask, if I work on this project for a few years, And if the result is negative, what will I do? And I usually come back to my days in masters where I worked on deep learning for that so long year and result was negative, and it's still worthwhile. So that's like what motivates me to work on problems. Yeah.
And then the last question, it's sometimes the hardest. If you could come up with one piece of advice for
Mhm.
a new researcher who's just getting started, and it can kind of be a useful heuristic or it could be some grand summary advice.
Mhm. Yeah, for new PhD student, I always want to say that, the good part of a PhD is you have 5 years, right? And although the process can be stochastic, like 5 years is a long time, so that if you're committed to something, you can afford to try things that you don't dare try before.
Mhm.
So I think that is something that I usually like to see, and try, and be bold, and usually there's something fun and new.